Welcome to this presentation on a reference quench probe, a new tool for in-situ quality testing during quenching of through and case hardened steels. This presentation in three sections is intended to give an overall view of the hardware and the software features. Before we take up the hardware features of reference quench probe in this part of the presentation, let us look at some of the existing probes that are available to the industry for obtaining the cooling curves. There are a number of probes developed and used regularly by the industry with different materials and different shapes. Now, these probes are of standard material. It could be an austenitic steel as used in the Lisic NANMAC probe, or even a silver probe. The ASTM standard probe defined in D6200 is an inconel probe. There is also a Grossman probe with SAE 5145 as its material. These probes generate one cooling curve at the center of the specimen, and they are generally generated in a laboratory using a sample of the quenchant in static conditions. As different from these designs, the reference quench probe is made of the same material as the component being quenched, and also the quenching is done in the laboratory, not in the laboratory, but in the plant. So it considers all the factors that influence the quenching operation, like the alloy being quenched through its different materials, and also the latent heat that is liberated during the austenite transformation. And on the quenching side, the agitation in the tank, the usage factor of the oil, and a host of other things which are not considered during laboratory generation of the cooling curve. Now, it has been proven that quenching characteristics of an alloy are dependent on the steel as well as the quenching oil, not only in the type of oil, but the agitation that is imparted to the tank. As an example, we will consider an industrial cooling curve that is obtained using this quench probe. This curve was obtained during quenching of an alloy steel in an industry. The important thing to notice here is the very slow cooling rates at around 420 degrees, which is due to the latent heat liberation during austenite transformation at that temperature. Now, such details of the cooling curve will be totally missed if a standard probe made of a different material other than the component being quenched is used, and that too in the laboratory conditions. Hence, the reference quench probe is developed to overcome all the deficiencies in the present design of the various quench probes. The hardware consists of a handheld unit which is portable and which has an integrated design for measuring the temperature at the middle of the specimen, collecting the data and storing it in a data logger, which can then be downloaded to the computer for further analysis. Now, the probe comes with a portable furnace which can be deployed in the plant, which can be moved near the quenching tank, and hence the actual conditions during quenching is captured through the arrangement. An analysis of the cooling curve, which is essentially a process signature, is done later through a very well developed and tested software. In the second part of our presentation on reference quench probe, we will touch upon some of the important features of the software. What you see on the left hand side is the mathematical representation of the cylindrical quench probe. Now, the dimensions of this quench probe is 25 mm diameter by 125 mm long. For mathematical purposes, we consider only the central 6 mm disc shaped part with the thermocouple located at 4 mm from the surface as shown. This rectangle shown here is essentially 1/2 of the disc on the right hand side. Now, the left border of this rectangle coincides with the axis of the specimen, and the right border comes in contact with the quenchant. The position of the thermocouple is shown here, marked TC1. There are 8 virtual sensors located at important locations. The entire disc is divided into 5 regions. The central region is the base metal, and subsequent 4 layers constitute the total case. In this case, we have arbitrarily chosen the case thickness as 1.92 millimeters. This 1.2 millimeters total case is divided into 4 equal sublayers, and the composition of each one of these layers, including the core material, is input to the software. Now, you will see that the base material composition is given here as carbon 0.29, silicon 0.299, etc. The other critical data that is required for calculating the CCT diagrams for this steel is listed here. It constitutes the AE3, AE1, binary start, martensite start, martensite finish, and other important data. As you move towards the surface, you will see that the carbon percentage increases from 0.29 to 0.35 to 0.45 to 0.65 and 0.85 on the surface. Corresponding to these chemical compositions, the TTT diagrams are also generated, which can be seen here. Now the core material has a TTT diagram described in this fashion with the ferrite curves, ferrite start and the ferrite end, with the pearlite curves defined in this fashion and the bainite curves defined in this fashion. As you move towards the surface, you will see that the TTT diagrams move towards the right, indicating that the steel becomes more and more hardenable. Hardenability of the steel or the sublayers increases towards the surface. For example, here at the medium carbon level with a carbon percentage of 0.45, only the pearlite and the bainite phases are expected. The high carbon steels and the surface steels are also defined in this fashion. Apart from TTT diagram, the hardness data is also input as a model for the calculation of hardness of these sublayers. You will see that the carbon, depending upon the carbon percentage, the model also varies, however slightly. The properties are also defined in a similar fashion with the density, thermal conductivity, specific heat, latent heat, and the enthalpy of each one of these layers specified as functions of temperature. This constitutes the modeling of the materials. What you see here indicated in as red crosses are the virtual sensors. The virtual sensors will generate the CCT diagrams and calculate the yield strength and the hardness at those locations. For convenience, we have chosen one location in each sublayer and several locations in the core of the specimen. The third part of our presentation on reference quench probe, we will explore some of the features of post-processing that's available with the software. What you see here is the display of continuous cooling transformation at the 8 locations during quenching of the sample in an arbitrary cooling curve. We have considered 2 cooling curves for the analysis. One with the oil shown in blue has a typical slow cooling rate at around 420 degrees. The other one is a faster cooling obtained during polymer quenching. We will first show the features that were obtained during quenching in oil. The display here shows the cooling curve at location 1. The 2 curves that you see here is a part of the TTT diagram. Now at the surface, the cooling has been so fast that it has missed the nose portion of the TTT diagram. The pie chart here shows the percentage phases that are expected at this location. You will see that about 80% has been converted into martensite with about 20% remaining austenite. The hardness that can be expected at this location is shown here as 58.82, and the tensile strength expected at this location is 2131.8 megapascals. Now moving towards the core, TC number 2 has a different properties at the location. Because of the lower carbon percentage, the hardenability is slightly lower than at the surface, and the corresponding microstructure that is expected is shown here in the pie chart. Now that has slightly lesser retained austenite and slightly lower hardness compared to the surface, and slightly lower tensile strength. Moving away towards the center, TC number 3 cuts the nose, and you will see the point B marked here, which indicates a slight amount of the bainite forming at that point. And that's what is indicated here in this pie chart. About 5 to 6% of bainite is expected at point number 3, with a slightly lower hardness and a slightly lower tensile strength. Moving towards the core, a little more bainite can be expected, and because of which the hardness is reduced and the strength also is reduced. We can traverse the entire section of the specimen sequentially with the thermocouple located at the axis or the center of the specimen, indicating about 45 HRC and about 1418 MPa as the tensile strength. We will now move to the results that were obtained using the cooling curve obtained during polymer quenching. You will see that the cooling is faster, and it is natural to expect in such case a higher hardness and higher tensile strength. The post-processor shows exactly the same trend, with the austenite retained also reduced considerably. The bainite is totally removed from the core because of the higher cooling rates, and both the hardness and the strengths have been improved. We can show this as a bar chart wherein the variation of the hardness from surface to core and also that of the yield strength in the two cases have been presented. You will see that during polymer quenching, both the hardness and the tensile strengths have improved, and the considerable decrease in the hardness and the tensile strength from the surface to the core is also quite visible. A closer look at the cooling rates will give a little more insight into the process. You will see that in the case of oil quenching, which is the blue line, the cooling rate drops almost to zero at around 420 degrees centigrade, indicating that at that temperature the austenite decomposition to softer phases is promoted, and that's the reason why you get bainite in the core during oil quenching. However, in the case of polymer quenching, which is generally faster, you will see that a high cooling rate is maintained over a larger temperature range, and also it is considerably higher compared to the cooling grades with oil. Now, such insights can be obtained with reference probes, which is hitherto not possible. So today, the customer expects ever more stringent quality, and to be a leading player in this competitive market, the manufacturer has to adopt advanced techniques. Process modeling is one such tool. It provides rich information for better control. Combined with the practical wisdom of the industry leaders, we hope to increase the competitiveness of Indian heat treating industry across the countries.